Alright, for this lecture you're going to have a couple of questions that I'd like you guys to bring the answers to class so we can go over the ideas but not spend a whole lot of time doing the calculations. Alright, so basically magnets occur because different materials, the spins inside of them and inside their electrons don't cancel out. For most atoms, the electrons pair up, their magnetic spins cancel out, and each atom kind of is neutral when it comes to magnetism. But certain materials like iron, nickel, and cobalt have a natural magnetic moment. So every atom of iron, nickel, and cobalt acts like a little tiny bar magnet with a north pole and a south pole. And if you get those lined up, you get a bunch of small magnets all lined up together. You get a big magnet, and that happens with electric currents, things like lightning. Basically, there was the region of Greece where this happened a lot, so magnets are named after that place. So if you look at the magnetic fields lines, unlike electric field lines, are always loops. Okay, so it's always going around. It goes from the north pole of the magnet to the south pole of the magnet. The same thing happens with the Earth. All right, magnetic north is defined as the direction if you were just to hang a magnet and just let it kind of wiggle back and forth, and eventually it would line up and it would point toward the magnetic north pole. Now the magnetic north pole isn't exactly at the geographic north pole, but they're reasonably close. The weird thing about it is the north pole of a compass points to the Earth's north pole, which actually acts like the south pole of a magnet. So if you have the Earth, the north pole's up here, south pole's down here. North poles of compasses point toward the south pole of the Earth's magnet, which is at the north pole. And basically, instead of plus and minus, we have north and south poles. But you don't have any what are called monopoles. You don't have anything where it's just a north or just a south. And same thing we had with electric charges. North and north or south and south repel, where north and south will attract each other. Right? If you break a magnet in half, you just get two magnets. And if you break that in half, you just get another two magnets, and so on until you get down to the individual iron, nickel, or cobalt atoms. Alright, here we get to one of our more obnoxious variable names, magnetic field. The symbol for that is B. It's actually the magnetic flux density, but oh well, we're kind of stuck with this. So the units of magnetic fields are the Tesla, named after Nikola Tesla. But a 1 Tesla field is gigantic. The Earth's magnetic field is around 10 to the minus 5th of a Tesla. But 1 Tesla field is usually what they use to lift cars in junkyards, or somewhere if you've ever had an MRI. The magnetic field inside an MRI machine is usually between half a Tesla to 2.5 Teslas, depending on where they are. All right. Moving charges create magnetic fields, and vice versa. Moving electric charges have a force exerted on them by magnetic fields. So that force is going to be the product of the charge times the velocity crossed into the magnetic field. So if you ever have done vector products, cross products, you end up with a sine theta, where theta is the angle if you put the velocity if you draw the velocity vector and the magnetic field vector so they're tail to tail, theta is the angle between them. So the force is QVB sine theta. All right. To determine that direction, you can either write them out as vectors, three-dimensional vectors, take a cross product, is where you're finding the determinant of a 3x3 matrix there, doing all kinds of fun stuff, which I don't really want to do. Or we can use what's called the right-hand rule. And the reason it's the right-hand rule is just with the relation between the fingers we use are, work with the right hand. I'll teach you guys the left-hand rule that you can use later. It's slightly less appropriate, but that's okay. So what you're going to do, whatever direction the velocity is, north, south, east, west, up, down, with the paper, against the paper, right, left, basically you take your index finger and point it in the direction of the particle's velocity. Then put your other 3 fingers in the direction of the magnetic field. Now, if the magnetic field and the velocity are in the same direction, sine of 0 is 0, there's no force. But if you get a maximum there if they're perpendicular, sine of 90 is 1. So as it's going along there, you'll have that maximum magnetic field. So I'll show you guys a little bit of how to do that in class. Sorry for that little break there. Basically what you're going to do, let's look at this. So you take your right hand, kind of hold it up to the screen. I know you look kind of silly. Don't do this when there are a bunch of people walking around. You take your index finger, and for this very first one here, point your index finger up, curl your other 3 fingers toward the screen. And then if you look at that, your right thumb should point to the left. So that means the force is going to be to the left for this first example. Then if you do the second one, your index finger points up. Now what you're going to have to do is rotate your hand in such a way that you're not breaking your wrist, but then your other 3 fingers point to the right. The only way to do that is to have your thumb point toward the front of the room. And then your thumb point into the screen. Then for the third one, V and B, your thumb will point to your face. The fourth one, V and B, your thumb will point up. Then your thumb will point in for the next. So your thumb will point into the page and then out of the page here. So we'll go over those a little bit in class. See if you can figure it out based on what I have said there. And there's a practice problem I'd like you guys to attempt. So an electron goes to a region that has a magnetic field that points up with a magnitude of 0.2 Tesla, and it moves at a speed of 3 × 10⁶ meters per second due west. And I want you guys to see if you can figure out what is the force on that charge, magnitude, and direction. All right, thanks a lot.